Hello, I'm Anna Mackay, and this video is called Derivatives of Exponential Functions. So let's have a look at them. If you have the function e to the power of x, the derivative of that is, conveniently, just e to the power of x. If you're interested in a proof, you can look that one up, or just take my word for it. If you have e to the power of a function, essentially what you do is, I like to say, you copy and paste the function that you see, then, the e with the function, then you take the function and differentiate that part of it, so doing f dash of x. If you have an e to the power of a function, but with the coefficient out the front there, the derivative has the coefficient staying there. You copy and paste the e function and differentiate the power there, that function on its own. Let's put that into practice. So finding the slope function for f of x equal to these functions here. So we're going to be finding f dashed of x, that's the slope function. Now, first of all, 7e to the x. So we differentiate term by term. Well, the derivative of e to the x is just e to the x, and the coefficient stays there. So the derivative of that part is the same. The second part here, it's e to the power of a function. So we copy and paste what we see there, e to the power of negative 5x, and we differentiate the power. So if you're just thinking about that part there, negative 5x, the derivative of that is negative 5. And we can just leave it like that, don't have to simplify unless you're going on to use it further. The next one. So the derivative is, let's have a think. We've got the coefficient and a whole function here of e. So you copy and paste what you see. 3e to the power of x squared, take x. And then you need to differentiate the power. So the derivative of that would be, have a think, 2x take 1. Making sure you're using brackets here. This one here, you're going to have to use one of the rules that you've learnt in previous videos, thinking what that one would be called, that rule. It would be the chain rule. So the derivative of that needs to use the chain rule. So you need to bring down the power and then copy and paste what's in the bracket, lower the power by 1, and now you can differentiate the inside. So differentiating an e function, you copy and paste what you see using brackets, and then you differentiate the power. So the derivative of 2x would be 2, and then you still are differentiating the inside of this bracket, but you've just got a constant left, so the derivative of that would be 0. So we can actually just leave that as it is. Moving on. Now, thinking about what rules you might need to help you differentiate these. Two that we've been working on, the product rule here and the quotient rule here. So let's do them. So f dashed of x would be equal to, you differentiate the first and leave the second. So the derivative of x to the power of 3 would be 3x squared, and you leave the second one. Then you add, where this time you leave the first, so the first function, and differentiate the second. So the derivative of e to the x is just e to the x. And that's our answer. Next one, using the quotient rule this time. Feel free to pause the video and have a go at this one, and then check back and see your answer, see if you were right. So I'll assume you've done that. So first function, second function, you differentiate the first. So you copy and paste what you see, and for ease you must differentiate the power, and then you leave the second. Now a subtract for quotient rule, where you leave the first and differentiate the second. So the derivative of 11x would be 11. All over, now 11x all squared. please do not write this 11x squared. You don't just square the final term, it's the whole of the denominator squared, so you must use brackets. Moving on. So our final example, and a little bit more applied. Find the gradient of the tangent to this function at a point. So the gradient of a tangent means we have to differentiate. So again, feel free to pause the video and give that a go yourself. I'll assume you've done that. So here's the derivative, dy by dx. Now first of all, I think we should write this function with a negative power as opposed to this, as opposed to what you see there. So I'd prefer to write it to the power of -1. Now again, what rule do we need to use here? The chain rule. So bring down the power, copy and paste what you see on the inside, lower the power by 1, differentiate the inside of the bracket. So the derivative of this is you copy and paste 2e to the power of 3x, and now you differentiate the power to get 3. And then differentiate the rest of that bracket, but that just becomes 0. All right, let's tidy that up. So thinking about what would be part of the numerator, this -1, and these parts here will be on the numerator, and the negative power goes to the denominator. All right, so there's our derivative. We need to work it out at x is equal to ln2. Now, when you sub in a value like that, it's actually much easier to use the function notation. So feel free to just change to that as opposed to the dy by dx. So let's just call that f dashed of x. They're the same thing. So now let's sub ln2 in for x. So we have f dashed of ln2, that's how I do my l's, is equal to, substituting that x value in to the derivative function. So we have -6 e to the power of 3 ln2 all over, subbing that lnx or ln2 in where you see an x. Now let's tidy that up a little. So you need to be really good with your log laws here. So that's the equivalent of ln2 to the power of 3. And same in the denominator. Now, remembering your log laws, what that would simplify down to. I'll just pop it off to the side here. So this is the equivalent of 2 cubed would be 8, and that is the equivalent of 8. So it's going to simplify nicely. -6 times by 8, and in the denominator we'd have 2 times by 8, take 11, all squared. Therefore we have -48 on 16 take 11, all squared. 16 take 11 gives us 5. 5 squared gives us 25. Now, what I like to do is to check these equations, or these questions, on a calculator. Create yourself a visual as often as possible. So, first of all, this number here, let's know what we're heading towards as a decimal, because when we check that in our calculator, it'll give us a decimal. It's -1.92. So that's the slope of the tangent at x is equal to ln2. So let's check that. So a reminder with our graphics calculator to have the derivative turned on. So hang on a second. So I just now have to switch to my emulator. Okay, so we're putting in that function, which was, I'm going to put in 2. So I hope you've got your calculators there and you're doing that with me. You'll have a much newer version than this calculator here. All right, and enter that. Now, if you were we need to check that the derivative is on, so we're going Shift Setup, and we're coming down here, making sure that derivative is on. Now, if you were to draw that, You may have seen a tiny little thing happen there. Let's zoom in on that. So our standard view window is -10 to 10. Let's just go -2 to 2. And same with the y, -2 to 2. Scale of 1 is fine. Draw that. So we get a better idea of what we're dealing with. Remembering this straight line here is just the limitations of the calculator, and it's drawing that asymptote. Okay, so if you use the trace function, you can find the derivative value. So shift, trace, and you start typing ln2 for our x value, hit enter, and here we are. Our dy by dx value is -1.92, and that's what we were hoping for. So it's a really nice way to check before you finished a question to know if you've got it right or not, and to create a visual of what that might look like. Okay, so that was the end of this video. If you liked it, give it a thumbs up and subscribe to the channel, and the next video in the series will be called Derivatives of Logarithmic Functions. Thank you.